Let's derive the centripetal force formula. Here we have the mass on the string going around in a circle. In a short amount of time, it's going to rotate through an angle theta. The velocity was pointed this way, is now pointed this way. This distance s is the arc length. If we look at this in a very short amount of time, that arc length starts to approximate a straight line. I've just put the velocity vectors tail to tail. That's the first velocity vector, that's the second. They're not changing in magnitude, they're changing in direction. This is the vector that represents the change in velocity. The angle between these two velocity vectors is also theta. The velocity must always remain perpendicular to the radius, so that if the radius rotates a certain angle, the velocity follows and rotates the same angle. You can demonstrate that with a piece of paper. The velocity is at a right angle to the radius, and if I rotate the radius, I rotate the velocity. It's the same relationship. Well, you might notice now that we have two similar triangles. So I'll say delta V is to S as V is to R. Now, which V? It doesn't matter. We're only looking at the magnitude here, and they both have the same magnitude. Well, it's going to take a certain amount of time to go from here to here, and that'll be the same time to go from here to here. So I'm going to divide by delta T on this side and delta T on that side. I'm going to bring the S over here, and now I have delta V over delta T equals S over delta T times V over R. What's S over delta T? This is V. The distance the ball travels in that time is how fast it's going. So I have V squared over R equals the change in velocity over the change in time. Well, boy, does that sound familiar. That's acceleration. But how can we have acceleration? The velocity hasn't changed speed. I mean, if the ball is going 5 meters per second here, it's going 5 meters per second here. So what's the deal with the acceleration? What's with that change in velocity? This is the change in velocity towards the center. We're not changing speed, we're changing direction. This change in velocity gives us an acceleration due to a change in direction. The change in direction is towards the center. And that's what we call centripetal. So this acceleration gets a letter C for centripetal, or towards the center. So as this ball moves around, it's accelerating towards the center. So what causes that centripetal acceleration? There has to be a force. And we label it with a C. It's towards the center. So how can I calculate that force from the acceleration? We have a mass, F equals ma. If the acceleration is towards the center, the force is towards the center. And here we have the centripetal force formula. Now remember, you can't leave the diagram like this. We always have to state what causes the FC. In our lab with the ball on the string, it's the tension in the string that pulls it inward. So let's say the radius was 60 centimeters, the mass was 80 grams, and we have a velocity of 5 meters per second. What's the centripetal force? We make sure we're using kilograms and meters, and we have a centripetal force of 3.33 newtons. That's how hard you would have to pull to maintain the circle. What's causing that? The tension in the rope. Now, this is all theoretical. You do an experiment to find out what it really reads by looking at the spring scale on the apparatus. So here's the apparatus. We've got it set up with a 60 centimeter radius, and the mass was 80 grams. But how do you measure how fast it's going? We time it over a distance. We can measure the time it takes for one rotation. Well, that would be pretty silly because it's going to go pretty quick. So we suggest about 10 rotations, and you can time that. Some kids put their camera down here, videoed it, put it on YouTube, frame by frame, and just did one rotation. If you're doing frame by frame, that'll be okay. You'll get a good number. Let's just say it took 8.2 seconds to go 10 rotations. We get about 4.6 meters per second. If I say that tension is what's causing the centripetal force, I can calculate the tension. Now remember, we're going to say the tension is what's causing the FC. Now we'll see what happens to the tension when we change the speed. We'll make a little data table. We'll measure the velocity in meters per second, tension in newtons. We already saw that at 5 meters per second, we had a tension of 3.33 newtons. What would happen if I went a little faster? What would happen to the tension? I get 4.80 newtons. Now that's about as much force as this spring scale can read, so we can't change the velocity dramatically. For example, what if we doubled the velocity? Well, that's squared. So if you double something when it's squared, that should go up 4 times. And that would be about 13.33 newtons, more than what the spring scale can handle. Well, what if we went a little slower? We get 2.13 newtons, and that can easily be read on the spring scale. But if you cut the velocity in half, the tension should drop to 0.83 newtons. And now we're not going to be going in a circle where the string is horizontal anymore. That's so slow, this thing's going to sag a lot, and the experiment won't be valid. Besides, that's not a lot of force to read on this spring scale. So throughout all of these changes in velocity, the radius stayed constant. And now we can graph this tension versus velocity. I've labeled and numbered my axes, 0 to 10 meters per second, 0 to 14 newtons, evenly spaced, no gaps. Well, there's my data plotted. I also should include 0, 0.